All right, guys, let me have your attention. My name is Raymond Clark. I'm the faculty coordinator for the STEM centers here at MiraCosta College. And we have a tradition of, that started last year, of doing talks on the first Fridays of each month.
Okay.
And the talks are engaged with a couple different scientists, sometimes three, and talking about wide-ranging topics as kind of a dialogue, a fun dialogue that we want you to be part of that dialogue and ask questions and give your thoughts and insights to this. So the three people giving the talk today or leading this kind of event, there's Jeff Ihara from Biology Department, Caitlin Fisher from Chemistry, and Joe Solomon from Physics. So I'm going to let them take it from here and introduce their topic to you guys and lead the discussions.
Can I just say, feel free to sit closer. There's no splash zone. We're not going to spit on you or anything like that. Just feel free to come closer. It's
Well, I might.
Casual. Okay, maybe Jeff might. It's just a casual discussion.
Oh, and the event is being recorded for a podcast, so your questions can be recorded for posterity.
But still ask.
So don't say
Killed all
anything
questions that
incriminating.
were Thank you.
Yeah, so a few semesters ago, Joe and I were sitting in our office having really interesting conversations where he was helping me out with physics and we're talking about biological issues, and we thought that this is something that would be of broader interest than just what we were able to enjoy in our expansive office. So we thought, well, why don't we take this kind of conversation outside and make it available for other people to potentially benefit from or take part in. And so this is where the first Fridays came about. Was our general idea. And so it's entirely unscripted. The only thing that we sometimes have, we'll have a theme. We don't have any such theme today. So we're basically talking about whatever crosses our mind. I had to come up with some kind of catchy title to get you guys to come, which is how we ended up with the one that you guys saw on the poster. And what I have here is a list of topics that actually include the carbon tubes and carbon rings. But if anybody has come here today hoping that we're going to talk about anything in particular, because you really wanted to hear about something that happened really recently, feel free to add it to the list. Just raise your hand and we can send it back to you. Stephanie? Yeah. And I guess that's it. You guys have anything to add?
No, I think you kind of covered it.
Yeah. We're just going to talk about some science. So who doesn't like that? Come on. That's what we're here for. Let's talk about some science. Learn some cool things today.
Yeah. Start with one of the cool things that happened was the gravitational wave detection. I'm going to get this wrong, okay? Because I'm a biologist, and Joe's just waiting for me to stumble. And so gravitational wave detection of a new phenomenon. This would be a black hole colliding with a neutron star. And maybe Joe could tell us a little bit about LIGO, Virgo detectors and what they are. It's like the most incredibly cool thing in science that I'm aware of. And I'm a biologist, and it's not even related to biology. So I'll let Joe explain it.
Sure. So LIGO, Virgo, what's the other one? And LISA is an ongoing one too. But they're all detectors that. Okay. Where do we start? So Einstein, right? That guy? Yeah. So he said that basically gravity is distortions in space and time itself. Okay. Yeah, it sounds sci-fi and abstract, but we've kind of confirmed that it's true in a lot of ways. And so one of those predictions that came out of his theory was the fact that gravity can cause little ripples in space and time. So if some giant catastrophic event happened out there in the universe, gravity would kind of ripple away, and you kind of feel the effects gravitationally. So maybe the Earth might get sloshed around a bit. All right, but gravity is really weak. So generally, the waves we feel from those huge distances, it's like less than atomic scale perturbations of what we would actually notice here at our scale, at our level. So the LIGO, Virgo detectors, and LISA eventually, whenever that comes online, what they're doing is they're basically shooting out laser beams for like a couple miles in perpendicular directions, all right? They have really, really, really fine-tuned mirrors that are very precisely angled so that that one beam will bounce back a few 10,000, 100,000 times, okay? So it's going overall a few 100,000 miles over and over again. That takes like a couple seconds for light to do, right? Because light goes really fast. By doing that, and by just waiting and waiting and waiting and waiting, they can kind of see perturbations of atoms at the scale of a fraction of a proton size. So for actual distances that we're talking about here, so an atom's about like what, 1 angstrom, right? A couple angstroms, right? So 10 to the negative 10 meters, right? 0.000, a lot of 10 zeros and something, some number, right? A proton is 100,000 times smaller than that because the nucleus is kind of squashed right in the middle of the proton. So that's already 10 to the negative 15 meters. These perturbations, these little blips we're seeing from gravity kind of rippling, are about 1,000th to less than the size of a proton. So we're talking about 10 to the negative 18, 19-ish meter kind of fluctuations. And that's the level of precision that these detectors have to reach to even see anything. Not even get good data necessarily, but even see anything. It took like 15 plus years of troubleshooting to kind of even get something out of the data. We saw our first detection like 2 years ago, which is super cool. We saw 2 black holes colliding and merging. We didn't really see it directly because you can't really see a black hole. That's why it's called a black hole, right? But we saw the gravitational signature, the kind of little blip instead of the huge blast, as if if we had been there a lot closer. And this one's really interesting, this black hole neutron star one, because black holes merging with black holes, well, two black holes merging become one big black hole. It's kind of not that interesting, right? Because you just have a hole in the universe and a hole in the universe, and now it's a bigger rip in the universe. Okay.
That's kind of cool.
Kind of cool, right? But what's really cool is when matter starts to interact with black holes, because then you start to get a lot of interesting effects. You can see what kind of radiation is thrown out. And because there's so much energy involved, you can accelerate matter like way faster than what we can do on Earth. So we can use those to kind of probe the universe at the really high energy levels that we can't really get to necessarily here. So being able to see that gravitationally is interesting because we don't even know what neutron stars really, what they look like. We think they're just like one big neutron, basically, from a lot of neutrons acting together cohesively, but we don't really know what their structure is. We think they have earthquakes, but we don't really know either. So things like that will give us little probes into the structure of neutron stars.
There's a whole bunch of neutrons interacting.
So it's kind of crazy.
Yeah, I want to hear about
Let's
this.
talk about neutron stars because they're actually really cool. So stars, if they get too big, will collapse because they're just so heavy. Gravity just kind of wins and kind of starts crushing them and crushing them and crushing them. That's how black holes happen, right? Gravity crushes it so hard, it literally rips the universe open. There's a hole in where you can exist in the universe now. Neutron stars are that kind of in that final phase, just when the star is pretty heavy, but not too heavy. And so all the normal matter that's there, like the hydrogen, helium, all that stuff that's in the star, gets crushed so hard that the electrons are crushed pretty much into the nucleus, and the protons and electrons kind of go through a reverse beta decay basically and become neutrons instead.
Wow.
So they all get crushed to that point of all becoming neutrons, and because they're all crushed so tight, it's like one big quantum state, we think, but we're not sure.
Right.
So they're acting like one giant neutron, basically, overall. And it's super weird to think about because it's like one big nucleus just floating out in space.
Is it stable?
Mostly stable, yeah. There's some that emit radio waves randomly because we think that it's spinning so fast and there's like glitches, so you get little earthquakes happening and then radiation just flies out. But for the most part, pretty stable.
So it's like a strong force then.
It's like a giant, strong force held
So
ball.
anyone doesn't know what I'm talking about. If you've taken me for Gen Chem 1, you know what I'm talking about. So, right, the nucleus is held together by protons and neutrons interacting through the strong force, right? And it's super, super stable. If you obviously crack an atom in half, you get nuclear fission, which releases a lot of energy. So I'm just trying to imagine that on the scale of a star, and it's like hurting my brain a little bit.
Because it's the strong force which is attracting, but gravity's so strong it's rivaling almost the level of the strong force too. So, yeah, this stuff is super dense. It's hard to explain how dense it is. Like, if you think about an atom, right? Again, we said it's 10 to the negative 10 meters, right? The whole thing. The nucleus is where most of those masses you see on the periodic table, most of that mass is in the nucleus, right? And that's 100,000th the size of the whole atom, right?
I have
So-
an analogy for this.
Go ahead. Yeah.
Okay.
Yeah.
So again, back
Yeah.
to bad analogies. But if you imagine like an atom is the size of like Qualcomm Stadium, which
Yeah.
is like very big and sadly empty these days. But so right, and then you take a grape and you put it in the center of Qualcomm Stadium. That grape is the nucleus, and yet the grape weighs the same as the stadium. So take like however many tons and tons the stadium weighs, condense it into a grape, and then put that in the center of the stadium. That's what an atom is. So
Yeah.
it's kind of quantum gets weird, gets real wacky.
Yeah.
But it's interesting to think about, right?
And it's so much mass in so little space that, like, if you could go to a neutron star, let's say you could do that. Let's say you could land on the surface. If you could pick up some of the dirt, right, the soil on there, it'd be pure neutrons, and it would weigh like a few 100,000 tons if you picked up like a little teaspoon amount, right? That's how heavy and dense and compressed and insane this kind of star is. So
Don't try it.
don't try it. Probably die on the way just landing there. But that's why we like neutron stars, because they really let us probe how kind of everything we know works in a lot of cool ways. And black holes are, well, just cool because they're literal holes in the universe, right? So, yeah.
In between the first discovery of the first detection of black holes colliding
Yeah.
and the most recent result, there were other results where you had two neutron stars that were colliding. And once we had the Virgo detector, we were able to pinpoint the location where the waves would be coming from. So I think they're able to detect through light emissions of neutron star collisions, or am I mistaken about that?
So I believe Virgo and LIGO can detect things just through the gravitational wave emission. So, and LIGO has two locations. Virgo has one, I believe. And I think there's one more gravitational wave detector I'm forgetting about. But between the 3 and 4 of those that are out there, they can pinpoint pretty much where something is to fairly good
And
accuracy.
so at that point, you can turn your telescopes there and
Right, so yeah, this is how the setup has been working the past few years, because we've been able to figure out where these things are coming from now. So generally gravitational waves kind of just fly through space unaffected, because it's literally space itself rippling, right? So the gravitational wave observatories will say, we think we found something, send a message to all the regular detectors that use light or radio waves and stuff, and then all the telescopes that have time will just like turn to that location and wait to see how light is getting affected and what actually reaches us here. So we can kind of see a delayed emission of X-rays and other stuff that might be flying out too, if we're lucky and if things are oriented the right way.
But you wouldn't be able to do that with black holes, or could you do that with black hole collisions?
You could as well, depending on how much matter is around the black hole and what exactly is near it. Because black holes themselves, again, just literal holes in space. So we wouldn't see much unless there was some other matter that could get heated up or pick up some of that energy and then emit radiation as a result. So yeah.
I have a question.
Yeah.
So if like two neutron stars collide or two black holes collide, is that just like a traffic accident, like happenstance, or are they attracted to each other? Like what, can you predict their trajectories? How would you know? Or they just kind of happen? They're like,
Yeah,
oh,
I mean, they are attracted through gravity, but if you think about a galaxy made of stars and just them swirling around or things moving around, there's a really low chance of two things colliding.
Yeah,
randomly
right, exactly.
From
So-
all the velocities that are kind of radially moving everything around. So it's mostly happenstance, but in the center of the galaxy, there's so many stars, there's a higher concentration that probably goes up. Not like a whole amount, but enough that it's a noticeable difference from us all the way out here. We're kind of in the far arm, kind of edge of the arm of one of the galaxies, Milky Way's spiral arms. But towards that core, towards that center, it's much more likely. And that's where we tend to see most of these things.
so you can make predictions like, hey, in 5 years, these two are going
kinda,
to collide.
kind of, yeah,
Okay,
kind
because
of.
that seems like a really lucky guess that you have something pointed at the universe and like, oh, look what's going to
Well,
happen.
and that's the beauty of the gravitational wave detectors. Like they're both. So LIGO again has two. One is in Washington. One is in I want to say
Louisiana.
Louisiana. Yeah, that's right. And so they have two perpendicular arms of lasers, kind of oriented in such a way that if anything kind of flies by us, we pick it up, no
Oh.
matter where it's coming from.
Right.
So it's constructed so that we can kind of feel something almost no matter what.
Oh,
In
okay,
a sense,
okay.
yeah. So it's not just like pure luck.
Because I was going to say, that would be amazing.
It was great though.
Super
When
lucky.
they were first trying to like put the detectors online, and they're like, "Okay, it's ready. We're good to go." Like I don't know, 12 years ago now or something.
Nothing happened.
And it was just like, "Oh, it's just noise. We can't see anything. Shit." So we have to start again and figure out how we get rid of all the noise. They were picking up like cars driving by on roads from a few miles away in their detectors because they were so sensitive. They could see the car like on their detector. That's how much they could really do. And they even pick up earthquakes all the time. Like even like very low magnitude earthquakes that regular seismographs can't actually pick up. So yeah, it's been a fun, crazy, insane science like game, basically trying to get that thing to work.
I bet.
Yeah.
Got a related stupid question.
Okay.
Okay, because this is totally sci-fi. And I might have to take one of the penalties for this.
Oh, we're doing the peppers?
Yeah. Okay,
Should we explain the peppers? Okay.
well, yeah, if it comes to the point where one of us is embarrassed about something we say, we have to pay the penalty by eating one of these peppers. Just one. Right. And,
They're
and
fairly
and-
spicy.
and they're quite hot. If anybody wants to try one? Okay.
Front row?
Yeah, here.
Go ahead.
They're charapita from Peru. And watch the reaction.
How's it?
How's some kick to it?
Definitely hasn't kicked it. And so the Mars rover is going to have to power down for about a month because there's no way to send communications to it because it's on the far side of the sun.
Mhm.
Would gravitational lensing be possible to get communications to the Mars rover?
So you're saying by sending a radio wave kind of around the sun, it would bend in and kind of.
Yeah.
It would be, and we do see light get distorted by the sun, but it's such a minor effect that.
It's not heavy enough, or?
Pretty much,
Yeah.
yeah. I mean, the sun's really heavy, right? It's like 10 to the 30 kilograms. A lot of stuff there, right? But that's still like for gravity's really weak. I guess you have to keep that in mind,
Yeah.
right? So even with that much mass, the distortion you would get would be really, really minimal. I mean, I think the first observation of that distortion was in like 1938 or something. Some scientists just realized there's a total eclipse happening, and if they went to the right spot, they could watch the eclipse kind of around the kind of edge of the sun, and people could observe it somewhere else, and they could measure how off they were from their measurements in that location of the eclipse. And it was like 1/4000th of a degree or something like that.
Okay.
Very minimal effect.
So the sun would have to be a really supermassive black hole in order for it to
Right,
work out.
and there would be nothing here. Okay.
All right. So what do you think? Do I need to?
No, I think you're fine.
All right.
I think that's fine, that's fair. Right, do we all agree? Does Jeff have to take a pepper? Yeah. No, we're good? Okay, all right. Okay. Do any of y'all have questions? You've all been fairly quiet so far. No? Okay, just remember, we're just hanging out.
Would it be better to build a gravitational detector in space?
In space, that's exactly what LISA is. It's funny because people joke that the acronym is LIGO, the ground one. LIGO in space, that's what LISA stands for, yeah. So we're trying to build a trio or a quadruplet, I guess, of satellites to act as a gravitational detector. And it would work pretty well because there's no Earth or cars or anything that would add to the noise of the detectors up there. But there's all these other problems, like how do you shield all that radiation from the sun and prevent it from destroying the satellites over time, right? All this other complexity. And just even launching that much stuff up there that's really sensitive is dangerous.
That kind of precision with the sun itself and push it out of the light. Push them out of the light.
That effect would be really minimal, and there are points where, like, we know our own gravitational map locally pretty well, so we have good spots where we could have a stable environment for those satellites. But yeah, the push from the sun's light wouldn't really affect it that much. It's such a minor thing that most satellites, it's not even something they really worry about.
Just figure since the precision has to be so great in multiple angles.
Yeah, I think because these things would be spinning too, it wouldn't really, like on average, it wouldn't really affect it enough to make a difference. Yeah, that effect that you're bringing up did affect, I believe, I think it was Voyager 2, which made it past our solar system a while ago. But over that super long trip over many years, the sun's light did accelerate in ways we didn't expect necessarily or think about when we launched it, like in the 70s. So, yeah.
So it would require 3 separate satellites?
4,
4?
space-time. Yeah.
Okay.
Yep, so, because, yeah, if we were talking about just a location, you would need only 3, but we want the time of the event too, from our
Okay.
perspective, so we need that 4th satellite to make that work. Also how GPS works, you would need at least 4 satellites up in space to make GPS work, because the time factor matters too.
But they're not going to be limited by 4 kilometers, the physical length.
No.
You could really set this up in
Right.
huge distances.
Absolutely, yeah.
Okay, it's like target practice. Aim a little laser precisely to hit that thing 4,000 kilometers.
Exactly, yeah. And even getting it to work on Earth, like, even just getting one arm of those detectors to work is insane. Like, the mirror has to be, I want to say it's cool to like 2 Kelvin. It has to be super cooled, so there's no thermal vibrations, like, all this crazy, crazy stuff. Super crazy. Like a huge engineering physics problem, really. But it's awesome that we got it to work eventually.
Okay. Moving on.
Switch topics, yeah.
Yeah.
Carbon rings.
Carbon rings, sure.
Carbon rings.
You already have that picture up there.
Yeah, that is interesting. So, was he talking about this in terms of like like battery and charge, or what?
No, I mean, I think the buzz that happened, it was like in August. There was major buzz because chemists had finally done this wonderful thing, which is to create a pure carbon ring structure, a flat ring structure, which apparently is some type of holy grail in organic synthesis. Or I had no idea they were trying to do this, but people were so nuts about it. I was wondering why.
So you say pure carbon, sorry, just to clarify, you mean no hydrogens, nothing, just carbon the whole way through
Only
in that
carbon.
ring?
And so the way it's
Okay.
apparently done is with triple bonds alternating with single bonds. And so, I mean, just from the standpoint of, not understanding enough about chemistry, why would it have to be that way as opposed to double bonds all the way around?
So, so I should give a little background on carbon, because carbon's great. We love carbon. Carbon is by far, in my opinion, the coolest atom on the periodic table. So it's the best one. And part of the reason for it is because of the way that the electrons behave. So, whenever people ask me, like, what is chemistry? I'm like, it's the study of electrons. Because we really just care about sort of how the electrons organize themselves to create bonds, because each of those bonds that you see, so I'll start with the single bonds, it basically just represents 2 shared electrons between the carbons. And then the triple bonds, the 3 lines, that represents 6 shared electrons. So the reason that this ring is a little crazy and interesting is because if you're in a lab and you're going to put carbons together in structures, they have sort of what we call preferred structures that are the most stable, the most energetically favorable. So, like, if you were to just like release a bunch of carbons together and be like, hey, make bonds, they're not usually going to make that because it's not their preferred like conformation. So, if you look at the structures that are next to it, you'll see there's a ring cholestane. I'm not sure what that is, but if you look at, there's a bunch of rings with 6 carbons or 5 carbons. So 6 to 5 is like the preferred ring structure for carbons, and you see those sort of motifs all the time. So like DNA base pairs have that ring in them, proteins have that ring in them. It's all over the place, and it's because when it comes to chemical reactions and chemical bonding, the most stable state is always the most preferred. So if you look at the ring on the right, that's way bigger and that's way shaped very differently than what you would find in nature. So the question becomes, well, how do you make something like that? And it's easy to be like, oh, you just go into the lab and mix things together and maybe eventually that'll happen, but you could be 200 years old and still trying to do that. So the idea, a lot of chemists, like, they like to be cowboys and kind of push the boundaries of like, what can I do and what can I synthesize and what are the applications of that? So looking at that ring there, the reason that it's very unusual is because the reason that carbon likes to make these like 6 or 5 ring structures is because the angles between the carbons are ideal. So what happens is those bonds have electrons in them. The electrons repel each other. So they tend to make these 3-dimensional shapes in space that get the electrons as far away from each other as possible, but also make it so that the carbon conformation is stable, right? So it's almost like, here's the modern dance portion of this, all right? So it's like, if this is like the most stable angle, if you stretch that angle out enough, it's really taxing on the carbon, right? So like at a certain point, if I try to get my arm behind my back, like it's gonna hurt a lot. So carbon's kind of the same way. It has these like preferred angles. That's not a preferred angle. And I think the reason that they were able to get this to work is because generally, if you have a carbon triple bond and then a carbon single bond, usually that wants to be linear, so straight across. So what they might have been able to do is, by having, I think, 18 carbons or however many they have in that ring, they're bending it a little bit, but not so far away from linear that it's gonna like blow apart the ring. So I'm not sure what the application of this ring could necessarily be. It's cool to prove a point of like, look at how far we can kind of push the stability of carbon, and here are the structures we can make. But I will say one thing that's kind of cool about this is triple bonds are really interesting because they usually indicate that you have something called delocalized electrons. So basically that just means electrons that can go wandering, right? They can go off on like journeys. And that's a lot of times how carbon can be used to like conduct electricity, right? So maybe, but I think it's more just a proof of principle of, you know, we have these sort of natural parameters and things that carbon likes to do, which is 6 and 5, and let's see if we can just like really push the boundaries. How big can we make a ring? How far can we push the physical limitations of carbon? I think that's probably what they're trying to do, right? And sometimes science for science sake is okay. You know, it's like if you have the resources, you have the money. It's always, you know, people are always worried like this needs to have an application, and it might down the road, but it's also just cool proof of principle to be like, hey, we can do this thing. Like, look what we did to carbon. So, I mean, yeah, I think it's interesting.
Jeff's question though, the double bonds, why not C18 with double bonds the whole way?
So the double bonds would have a much stricter angle conformation than a triple bond. So
Because SP2 versus SP3,
yeah, so
right?
sp2, so double bond carbon basically looks like a triangle for the most part. So if you try to flatten out a triangle, that's gonna like, if you almost imagine like, here I come with a really bad analogy. Like take like 3 toothpicks and put it, like glue them together in a triangle and then try to flatten it without breaking the toothpicks. Like it's not really gonna happen. But if a triple bond, because it likes to be linear anyway, you could probably do this and it'll be okay. But if you have a triangle and you try to squish it, you're just gonna like break all the bonds into pieces. So probably that was the most advantageous way to get that shape, because that carbon doesn't want to be bent like that, but I think it's big enough,
big enough circle.
that it's
Right.
that it's making the angle small. It's like you know, it's like the curvature of the Earth is so large that it.
Right.
Okay, I'm not a flat earther, but like just saying, the curvature of the Earth is so large that when we're standing on the Earth's surface and you look out, it looks flat, right? It's not flat, but the angles are large enough. So I think that's what's going on here, right? It's like the curvature of this ring is large enough that the angles are going to be optimized to be like much flatter. And even like if you made it even bigger and bigger, then that angle would actually go closer to linear. So
I'm guessing this is at a good spot, right? Because the moment it's too big, so the thing about like circular or like flat molecules is generally they tend to want to twist up
Yes.
or collapse or do some weird thing.
Yes.
So they're not totally flat anymore. And what Caitlin said about the electrons, they're kind of localized along the ring, and that's keeping it fairly flat and stable. If you made this bigger, there'd be a point where the circle is so big and the kind of extra like bond strength, if you'd like, from the electrons delocalized on top, wouldn't be enough to keep it flat. So it would break or twist or do something else, most likely.
I mean, we see that all the time with ring structures,
Yeah.
like sugar, for instance, like glucose. That actually, so if anyone's taken organic chemistry chair boat conformations, that. So a lot of times, like sugar rings, they'll go into this conformation, they'll go into this this is neat. This is all my interpretation, right? So this is
It's a chair.
This is chair and this is boat. So the ring actually folds in on itself. So it's pretty impressive that they're actually gonna keep it flat. So yeah, they probably like optimized it. And I guarantee you there was some poor grad student that was in the lab and was like, oh, I gotta add another carbon. Oh, too many carbons. I gotta take away a carbon. Oh, too few carbon. Like you know that was happening. So
My mass spec was off.
yeah, exactly. Like, but yeah, it's pretty cool. Like I said, it's always I'm all about proof of principle sometimes. Like, a lot of times you'll come up with something and you'll do it, like, this is really cool. And maybe you don't know what the application is going to be until down the road, but that's okay. That shouldn't stop scientific, like, advancement and trying new things. So I would say at this point, that's probably a proof of principle of, like, energetics and bond angles and pushing the limits of carbon. But, you know, who knows? Maybe we could use it for something else.
Those roving electrons could be theoretically a superconducting material?
Could be. So typically for conducting materials, you usually see double bonds used more regularly because, so the only thing I would worry about is the ring is so big and it's not going to have a lot. So double bonds typically have resonance, which is sort of what allows those delocalized electrons to be used for conduction. Triple bonds are a little bit less effective at that, so I don't know. I mean, maybe. I wouldn't rule it out, but
I don't think it would be well. It would be.
It wouldn't be a
superconducting.
superconductor.
It would be at some temperature, probably.
Yeah, it
like
could
if you got
conduct,
it cold enough.
but
this probably still conducts well because, right, there's still a superposition of states you'd have between the triple and singles. They could
Yeah.
alternate, so it's like benzene
Yep.
in that it would be extra stable because of,
Yeah.
like if you swapped all the triples with singles and all the singles with triples, you'd still get the same molecule back. And quantum mechanically, that enhances your stability. There's multiple possibilities for your molecule to exist in. So I think it would still be fairly conducting in the, so it'd be conducting around this way, but not so much
No,
this
it
way,
wouldn't.
in this direction, like graphene and those other carbon
So the
carbon
conductive
structures.
electricity would go around the ring.
Right.
But the problem is like if you want conducting material like in a battery, you generally want conduction in like all directions.
Right.
So like in a Tesla, I believe they use carbon, and because they can build it where it conducts this way and that way, so that when you charge your battery, it's like going to store the potential a little bit better. So I don't know.
I think what maybe the application that people were excited about is like in terms of nanotech and building nanostructures, having a circular thing you can just lay down and that has electrons on the top and the bottom,
Yeah.
so it's sticky, is really useful because now you can start just stacking things and making, cylindrical structures. You could make a capacitor probably out of that by kind of stacking a bunch of these together. So it's like making a nanotube, but a build your own nanotube in that sense.
Yeah.
Because nanotubes right now, we just kind of like what Caitlin said, we just kind of take some carbon and then kind of like get some tape and do some stuff and like, oh, we got a nanotube of this size this time, not of a specific size that we want. So
Well, and
this
then
is pretty cool.
Yeah,
in that sense.
and I'm not an organic chemist, but I mean, by training, I've definitely done it, but that's not my specialty. But I will tell you this: what I remember distinctly from organic chemistry is when you see double bonds and triple bonds, that is where you can do chemistry, right? So triple bonds and double bonds are really nice because what that means is that carbon has the ability to have some groups added to it.
Okay.
So if you see something like that, you're like, oh, look at all of those wonderful places that I could add on stuff. Like I could just like link things to the triple bonds, I could open them up. So I guess, yeah, if you think about like making like little nano robots and stuff, you have something that you can like start. That's my chemistry motion. Just do some chemistry. But yeah, you can start adding things to those triple bonds pretty easily, and you could potentially like scaffold upwards. I just don't know how great it would be for electrical conduction, but building things off of it, you could definitely do that.
I think it's pretty good because graphene is great along the plane of a graphene. So graphene sheets, just in case you don't know, it's just, graphite, like your pencil lead, right? It's just a bunch of carbon sheets stacked on each other. Graphene is if you could take one sheet off of graphite. So and this is how we first found graphene, really. If you take Scotch tape and put it on your pencil lead and peel it off, there will be little flakes of graphene on your tape. You might not see it with your eye, but you can see it visibly with other instruments. So if you imagine a sheet of graphene, of pure carbon, it's conductive along that plane and not so much this way. So I think this would be the same thing, just a smaller ring scale, and that makes
Yeah.
it useful in that sense.
So if you want to do chemistry at home, if you take a pencil and you scratch it on a piece of paper and put a piece of Scotch tape
Yep.
and peel it off, you'll have
Yep.
a Nobel-winning discovery. And I
Yep.
love to do science at home. Just throw a balloon in the fridge, watch it like contract, make some graphene. But yeah, I don't know about the conductance of this necessarily. But like I said, it's cool to. I think we're in a period of time where we're looking at 3D printers and nanostructures and making really, really tiny sculptures, for lack of a better word. So anytime you can make something that expands that ability to make cool three-dimensional structures, it's usually pretty exciting. So, yeah.
Well, the one thing that blew my mind more than the actual making of the structure was the fact that they took a photograph of it to confirm.
Oh, yeah. Scanning electron microscopy. It's so cool.
How do you take a picture of something that's like 18 carbons?
Well, you've seen that video of graphene, right? Like,
Yeah.
I think Intel took a video of graphene with an electron microscope, like over nanoseconds, basically, and they showed how like bonds were breaking and forming, and a missing hole of carbon was like filled in later by something else. So
That's a perfect example
this is
of
old
like,
news, Jeff. This is old news.
Well, but that's like such a cool example of
Yeah.
science it works because, so I love moments of science it works because for a long time we had predicted the three-dimensional shapes of carbon molecules. We're like, yeah, according to our calculations, it should be a 6-ring structure and it should have these bond angles, but we couldn't see it. And then scanning electron microscopy came along, and then they took pictures of molecules and they're like, that's exactly what we predicted
Yep.
based on, and I love that. That's so cool. We make these predictions.
Old news.
Yeah. That's cool news.
I just wanted to make him eat a pepper.
It's cool news though. It's very cool. It's very cool. So you can look up pictures of molecules online. Like just you can Google it.
Yeah, electron micro.
It's not the original scanning electron microscope, it's the scanning tunnel.
Yeah, it's
Yeah.
Scanning
been
electron microscope coats things with a thin layer of gold.
Yeah.
Bounces electrons off.
Right.
That wouldn't work because you're constructing bonds.
Right.
so you ate that pepper for nothing.
Does that mean Caitlin has to eat a pepper?
Do I? Oh. Fine. I'll try it.
Really, they work on the same mechanism though, because neither of those would really work without some level of tunneling and all that. So. Okay.
Yeah, if I wasn't awake before, I am now. Woo. No more mistakes to be made.
I guess just in case you don't know, electron microscopy, there's a certain point where we can't use visible light. Like the light we use to see things, we can't use it to see nanoscale things because our light has a wavelength that's too big to see stuff of that size. We have to use electrons, which act as waves at that scale, and that's kind of the whole, point of quantum mechanics. So that's what we use to see these things. We just shoot electrons. If they're the right energy, they'll have the right size, so to speak, to kind of see the bonds and atoms and let us visualize what these things look like.
Right. And it's that whole conundrum of, when you look at really small things like atoms and structures, when you look at things like atoms and structures,
I'll take one too, just to
when you visualize it, you're affecting it, right? Because those things interact on a quantum state. So yeah, when you visualize it, you're also affecting it. Good Lord. That's a spicy.
You want to try?
If you want to cry out of one eyeball, it's definitely, I highly recommend.
Oh. Pass them around.
Everyone's like, I want to join the party.
I mean, they taste good, just spicy,
Yes.
I do have a question with this.
Yeah.
With the carbon structure, after it's after it's built, are you worried about it randomly deconstructing itself? Like it being stable?
Well, I guarantee you that they did a kinetic study on it. So probably what happened is after they built it, they probably took it and looked at its degradation over time, right? So to ignore the crying out of one eyeball. So they probably looked at the overall, I know, what'd you guys do to me? That was so mean. So they probably had the molecule, and what you usually will do is once you create something new, you'll actually do a study where you look at its stability over time and its degradation, and then depending on, once you collect enough data points, you can actually extrapolate out how stable it is. So I'm sure that they check this, because there are a lot of things that are created in the lab that, are theoretically possible, but then they're not stable, right? So like even elements on the periodic table, we have ones that we made, but they're just like degrade right away. So there's a chance that this could degrade over time, but I'm assuming that usually if they report like, oh, we successfully made it, it has to exist for some stable portion of time. I don't know what that time is, but I'm sure they did a kinetic study on it.
Yeah, well, I think the scanning tunneling electron micrograph showed it adhered to a structure. Because you said it was going to be sticky on one side, right?
I think I said that. Yeah.
Right.
It's be sticky, yeah. This side and the back side.
Well, yeah, and I mean, if you build it on something else, that can help increase its stability versus if it's just like free floating in like a
Right.
test tube, you know? So if you like lay it down on a surface, that can definitely help kind of aid the stability versus it's like, you know, tumbling in 3 dimensions. Yeah.
And just one last thing about
Yeah.
that, which is, I mean, you guys been speaking about how they, you know, they designed this or created it, but how do you really manipulate carbon, which we're practically doing on an atomic scale? How do you really manipulate that? It's not like, you know,
Yeah, sure. There's a couple different ways. So the first way that you can do it is by utilizing particular catalysts. So if you're doing, so there's 2 kinds of synthesis. There's top to bottom, bottom to top, right? So bottom to top is you start with a single atom of carbon, or not a single atom, but you start with a smaller structure of carbon and then you add to it. And you can also start with a larger structure and then you can pare it down. But usually that's going to involve some kind of catalyst. So the first thing they could have done is they could have used a particular catalyst that sort of made this process more energetically favorable. And probably what they did is they added some sort of carbon reactant to it. Could be something, I mean, I don't know for sure what they used, but they could have used like methane or maybe, actually probably what they used was ethylene, yeah, which is C, triple bond C with 2 hydrogens, and then they could replace that hydrogen with another one, almost like a polymer, right? And you can use a catalyst to do that. So that's one way you can do it. The other way you can do it is you can almost like a 3D printing type of thing. That's how they tend to make like nanotube structures. My guess with this is they probably used a catalyst and almost treated it a little bit like a polymer. And there's ways, so you can add different like groups onto this that direct your chemistry, right? So let's say you have this ring and now it's a long strand and then you want to close the ring. You can put little groups on the ends of the carbon that help site direct the closure, and then you can use a catalyst to make it happen. Chances are they tried and failed a lot with this because even with a catalyst, this is kind of not what carbon particularly likes to do. So my guess is at the end, they probably had a soup of all of these different carbon compounds, and then they pulled out this ring, and they're like, we got one.
Because I'm guessing
yeah.
like C18 to C20,
Right.
it's not going to be that much different in terms
Right,
of its
right.
properties. So
Yeah.
I wonder how they selected for this one specifically.
Yeah, so site-directed synthesis is what it's all about. It's using a catalyst, and it's using these like little group linkers to be like, hey, we want these 2 carbons to connect. We're going to put a group on there that makes it favorable for them to chemically combine. So probably this was like, I'm just like being conservative here. This was probably like a 30 to 40 step synthesis, probably, at least. And then probably at the end of that, they had, like I said, a soup of all these carbon compounds, and they're like, we got one. But I doubt they had like, 98% yield. It's like I don't think they had that, right?
Probably like 0.1.
Yeah. So that's the thing in chemistry is if you're making something that's difficult, there's 2 steps. You prove, yes, I can make it. And then the second step is I'm going to try and increase the amount that I can make. So probably now they're like, okay, we made this. We made very little of it. Let's see if we can like make this more energetically favorable so we can make a lot of it. And that's the hard part, to be honest, I think. Yeah.
Awesome.
Would there have been any way they could have used atomic force microscopy to manipulate atoms? It's too small a scale for
It's-
tweezers.
I think that still would be too.
I don't know if it would have been worth it. I think maybe it would have been difficult to do. And I think also, like I said, my likely feeling is that this was like a big soup of all of these different compounds. And so trying to isolate out just the one you want to use AFM on would probably be pretty difficult. So I'm guessing, and they're probably not going to tell us what they did because they want to make it proprietary first. But I'm guessing it was definitely going to be something more site-directed synthesis. But maybe once you're able to scale it up and you know exactly what groups are going to work to link this all together, maybe you could implement that. But like I said, if it's like it's like you have minestrone and you're like, I'm going to pick out all the pieces of tomato and then like try to do chemistry on it, that can be really, really hard. So.
What do you think they might use this for in the future? Like, what's the I know that you said they made it to just make it to say
Yeah.
they made it.
Yeah.
But do you think that there was any other thought process besides just like them?
You know, from my experience in the field of research, probably they weren't thinking that far ahead. I'm not meaning that as a diss. Like, a lot of times, you know, when you're in the lab and you're studying something and you think it's really cool and you're like, I want to prove this principle, a lot of times the applications come later. So that wasn't probably the first thing on their mind. But kind of like we said, I mean, there's a potential that there's like this kind of push to make like different carbon structures and like build things and it's almost like if you imagine like you're going to build a house, you always start with the foundation. So the cooler you make the shape of your foundation, the more you can like make a crazy house out of it. So maybe this is just like a foundation that they're going to maybe then build things off of, because like I said, triple bonds are super, super reactive and you can always add things. So it's like you have that triple bond, you can just like pop it open and then add things to it and you can kind of build up. So, you know, who knows? I think there's lots of possibilities. But in terms of did they have something specific in mind, I doubt it. And I said, not a diss, not at all a diss.
I mean, I see it as a possible building block for other nanostructures. So if you just imagine stacking these, you could imagine making like a direct connection, like a wire almost, between two structures, right, that are atomically sized. And I think now that we've talked about AFM and tunneling microscopy, right, this might be a really good way to isolate tunneling effects, because electrons like to just zip around and be where they shouldn't be at the quantum level, right? So if you have these bonds that are kind of isolating the middle from the outside and you have a bunch of them stacked up, you could maybe shield that interior of that wire from other electrons that would otherwise tunnel in to some extent. There's enough potential energy in that layering of bonding to prevent
Make a little
that.
cage,
Yeah.
right? And
'Cause-
then
yeah.
you can direct things through the middle.
Right.
Because I think that's like goes into like the quantum computing and
Absolutely,
things like
yeah.
that.
Like Intel has tried to make nano circuits for a really long time now, and the main obstacle has been our electrons don't stay on our nanowires because quantum mechanics. They tend to like leak off and fly off somewhere random because they can. So things like this might actually help us tackle those issues, and it'd be cool to see where this goes, because it's a really nice building block. It's a nice circle.
Because yeah, you want to keep, like if you're going to use electrons and you're going to use quantum mechanics to like conduct, you know, like for lack of a better word, like signals or information through wire. If the electrons are just like disappearing
Yep.
somewhere, that's not helpful. And so, but I think because electrons are, you know, they have some repulsion. So if you put them inside, theoretically, a cage where there's like negative charge all around, and like if this is delocalized, then what's going to happen is this ring is just going to be one big negative charge, and electrons don't want to necessarily get close to that. So if you have a big negative charge on the outside, they're going to want to stay in the middle, hypothetically.
So it could give you the ability to direct them
Yeah.
where you want them.
Yeah.
I could see that. Yeah.
Which is very, very hard to do.
And that's probably also why people were freaking out about the battery aspect of it, right? Because if you have that ability, then you can make nano-sized batteries, and that's like I guess holy grail really is a good word for it. Because we've been trying to find good components to make nanocircuits reliable. Because we can make regular sized circuits easily, microcircuits really easily, but the nano has been lacking. And that's once we have that, I think like the technology we could access would just kind of
You could have a
explode,
phone
like
that's
just
this big.
completely explode.
You have an itty bitty little iPhone.
You could have nanorobots in your body that fix you all the time. I mean, like the possibilities are just endless at that point, So, yeah, cool stuff.
Oh, yeah,
Yeah,
John.
along with using the nano battery power to make smaller and smaller technologies, would it also help make more effective batteries?
Yeah,
Yeah,
definitely.
for sure.
Absolutely. Yeah.
Yeah, so the biggest problem with battery technology right now is that the batteries wear out over time. And the reason for that is because, so those of you who have taken Gen Chem, you're gonna hear this, you're gonna be like, oh, again? But basically, when you charge a battery, what you're doing is you have an influx of electrons. And so like, for instance, lithium ion batteries, when an atom picks up an electron, it expands, right? Because the electrons are now repelled from each other. And so that expansion and contraction when you charge your battery ends up messing up the alignment of your materials, and then it wears out your battery. But with things like carbon, we don't have the same problem because the electrons are delocalized, so you don't get that expansion and contraction. And so the batteries don't wear out as fast. And in fact, like I said, Tesla is using it, and their battery life on their battery is actually pretty good compared to like a straight lithium ion battery. So yeah, if we can if we can make batteries that are smaller but more reliant on carbon, that's going to be really helpful in not just the efficiency, but also like the lifetime of the battery, because you won't get that expansion, contraction, and then a crack in
And
your
then
materials.
I think also carbon, right, has a lower thermal conductivity and expansion coefficient. So even if carbon does expand and gets hot from usage, it doesn't expand as much as a regular metal would too. So yeah, having something at the nanoscale that is carbon-based would be pretty good.
Because metals, in addition to being very conductive of electricity, are also very conductive of heat, which everyone knows if they put their seatbelt on in their car after a really hot day, you touch your skin, you're just like, ah, right? So, but carbon on the other hand, I mean, if you leave pencil lead on your dashboard, it's not gonna like heat up to the point where it scalds you.
Right.
Metal will. So it's kind of, you don't want your computer melting when you're like doing work. So, or your car engine melting when you're on the freeway. So, carbon works a little bit better for that because of its stability, its lack of expansion, and its lack of heat conduction. It's really much, much better. But it's just, the issue is scaling it up or scaling it down. We have like a little, either direction. Because we have this like little happy zone where carbon works really, really well, but then trying to make like bigger batteries is hard, trying to make smaller batteries is hard, and so we haven't really translated it yet. But as soon as someone does, they're going to win all the prizes and get all the investments, because that's going to be like huge. And I think we'll get there. We'll get there. Yeah. I'm also done crying. So
I'm so sorry.
yeah, no, it's totally fine. I wasn't that spicy. All of a sudden, I was like, my eye is leaking. So that's
And what do you guys think? Casey? Yeah.
Yeah,
no one else cried, just me? All right, well, that's fine.
a little bit.
Yeah, a little bit. It's like a little leaky. Yeah, it'll wake you up. Yeah, it's good. The flavor was really nice. More effective than coffee, I'll tell you that.
Okay, biology time?
Sure.
No, there are lots of really important studies. I thought the one that kind of caught my attention and kind of got deep into my my memory. I've always liked eggs, and there was this discussion about ethical eggs, and I guess the question was, well, what is initially unethical about eggs to begin with? And so we want to start with that part of the story. And you have to realize that any eggs that you buy that are made from female birds, and these birds are breeds that are not very good for meat. So in order for you to have a lot of egg-laying hens, you have to have a whole bunch of female egg-laying chickens, which means that every time that you have you breed these chickens, you're going to have to take half of the babies. You can determine the sex one day after hatching. You can you keep the females, and all the male chicks get thrown into a shredder, right? It's kind of disturbing to think what happens to all these baby chicks that are born. They're not, they could be raised for meat, but nobody wants these. They're not good meat breeds because they don't grow fast enough. And so the solution is to euthanize them or just to throw them in a shredder. And so the idea that people had was that if we can detect the maleness of a chicken egg before it's born, you could kill it at an earlier stage. You can use the egg as animal feed or for some other purpose. And so the challenge here is to make a mechanism, to devise a mechanism by which we can detect a male egg, a fertilized egg, shortly after fertilization, which can then, at which point it can still be used, as opposed to rearing it out, figuring out it's a male and throwing it in a shredder. Okay, I'm not a vegetarian or a vegan, but that kind of disturbed me.
I
Right?
feel really bad about that egg sandwich I had this morning.
Sorry, Caitlin. So there have been a couple of approaches. I mean, hypothetically, you could drill a tiny hole in the egg and do like a genetic test on the egg shortly after it's been fertilized, but that's not cost effective for the thousands of eggs you have to process. I mean, there were some real issues, and there was this biotechnology solution, which I thought was ingenious, and it involves genetically engineering a chicken such that, okay, the other thing you have to know here is that males in birds are the homogametic sex. With humans, with most animals, XX is a female, XY is a male. Whereas in birds and butterflies and a few other types, the homogametic sex is a male. And so if you have a female, it must have, every female must have got its X chromosome. Actually, it's called Z chromosome. But it's got, I'll use X and Y. Every female bird would have had to have gotten its X chromosome from its, so just make sure I got that right. X chromosome from its dad, because it would have to have gotten its Y chromosome from its mom. Exactly the opposite of what we have in people. Okay, so the idea here is that you genetically engineer bioluminescence, early expression bioluminescence in the rooster. Okay, so the genetically engineered part here is the rooster. And so if the rooster fertilizes, let's see. So what is this?
Just while you're thinking around.
Is the rooster gonna glow green?
Yeah, well, the male eggs are gonna glow green. You could pick them up with just regular visual inspection, and you could remove them, and then the female's eggs are not going to have the bioluminescence. They're not going to have the bioengineered bit, right? So the cool thing about this is it solves a problem, and at least to me, it also solves the issue of having genetically engineered food, because people are going to be recoiling from having GMO eggs. Technically, the egg is not GMO because there's nothing genetically modified in the content of the egg that actually hatches into the chicken, and then you'll be eating the eggs from that chicken anyways, right? So they're hoping that they can develop this and short circuit the otherwise laborious process of getting GMO foods produced or approved.
Wouldn't that only help large corporate farms as opposed to small farms? Because small farms don't do that sort of thing where they shred large amounts of male chickens. So I mean, it would only benefit large factory farming.
Yeah, I mean, if you, it would still affect, I think most smaller scale farmers are doing something similar to shredding. They're only rearing the female hen, the females, right? They're not taking the males and growing them out and eating them or putting them to some use. Yeah, well, if you're doing that, then no, you're not going to be benefited from this technology. But yeah, they're dual purpose birds. The birds that are actually reared for eggs are not very effective. They're not very good meat birds, at least for market
It
purposes.
depends on the breed.
Yeah,
I have chickens.
I do too.
I also work with people at the farmer's market that raise chickens for eggs and for meat. So I know that there's different breeds, they have the roaster, you can call them roasters, that are just giant birds that can barely walk by the time they're adults, and it's just because they've been bred out that way. It's not because they're GMO'd, but because,
Yeah, no, it's
hybridization is different.
they're far grosser than GMOs. A meat chicken, which is most of the chicken that you ever eat, is this monstrosity that grows into this gigantic chunk of flesh in 6 weeks. It grows to marketable size in a stupidly short amount of time. It produces a huge amount of crap. I mean, it's a totally weird thing. You don't really want to grow meat chickens if you want to like chickens.
I have egg-laying chickens.
Egg chickens look like regular chickens.
Yeah, they do. But I have roosters too. So I live in an area that can have roosters, and so we just get fertilized eggs.
Yeah.
And then as long as you take them out, within the first week, you don't have balut. You have, I don't know if you know what balut is. Filipino food where they actually.
That's not with duck.
Well, they do it with duck too, but some of them do it with chicken.
I like it.
You like it?
Yeah, that's pretty good.
But if you just take them out fertilized, you don't need to have that issue of even chucking the males. You just have males and females. I mean, if you start breeding out males, then what's going to happen? I mean, how are you going to have successive, mating going on? You just keep making a little smaller.
Well, you would have to keep, you would have to keep a stock of the glow-in-the-dark roosters.
So I guess my question is when do you pick up the bioluminescence?
What stage?
Yeah, what stage?
No,
yeah.
at the same time that you're candling the egg to detect fertilization.
Oh, okay.
So it's an early enough stage where,
Yeah.
where the egg is useful.
Got
Yeah.
it.
Yeah.
Got it.
But the egg gets too far along, then you have to throw out the egg.
Yeah, yeah.
If it hatches, then you got to just throw out the chick.
I love bioluminescence. It's so cool.
So I thought that was kind of neat that they're able, I guess to me, the big question is, well, how quickly are they going to make this provable? Because on one hand, we're gaining a whole lot in terms of ethical practices and animal husbandry, responsible animal husbandry. On the other hand, we're dealing with the general recoil to GMO foods. We'll see how this plays out.
Yeah.
I think even just a simple fact of waste, right?
Yeah.
You can then make use of half the eggs that you're hatching, basically, right? So that's even a simple enough argument in and of itself.
Yeah, but these
And ethical stuff, of course. I'm just making a simple point too.
but these eggs had a GMO grandfather.
Yeah.
Yeah, well, I very strongly feel like GMOs are demonized and not in a good way. I think that it's a little bit misunderstood, and I think there are definitely sort of under the umbrella of GMOs. I mean, almost everything that we eat is a GMO, technically. I mean, if you consider crossbreeding for advantageous traits, that's some people put that into a category as GMOs. And I saw this this documentary recently, and they were talking about beneficial GMOs, and one of them was golden rice, which is basically rice that's genetically modified to express high levels of beta carotene. And it's used to prevent blindness in countries that have lack of access to foods that naturally create beta carotene. And so it's kind of an interesting issue, right? Because I think, sure, with any advance of technology, there's always the potential for pitfalls, like maybe it becomes an invasive species or something like that. But I think that especially now with climate change, which is a thing, now with climate change, I feel like to create crops that are going to withstand the changes that we're seeing in climate, we have to implement GMOs at some point, or else, our food supply is going to.
You're not getting any argument from me. It's
Yeah.
just, but there's a reality of
Yeah.
this public perception.
I know, it's such a bummer.
But we could market it, right? We could say, hey kids, there's a glow in the dark egg. Do you want to eat that, right? Who wouldn't want to buy that, right? And try it. Like, come on.
I mean, apart from but we are getting rid of the glow in the dark ones. So.
Oh.
Oh, bummer.
Question?
Yeah, I was thinking about this GMO, because you hear a lot of this kind of rhetoric where you're like, oh, no GMO food, and I'm not going to sit here and say that I know anything about GMOs, but how do you kind of change the perception, and then how do you responsibly implement these to the public without long-term studies of what this GMO food is doing to the human body? Because cancer is on the rise. These things are on the rise, and people want to demonize things because we don't want to have cancer. We don't want to have these health problems.
I think. Oh, go ahead.
No, I mean, it might be. I don't think we've made enough of a deal of the benefits of GMOs. I think if we were to do something that really benefits humankind in a really obvious way, I think there would be more acceptance. I mean, if we were to be able to get rid of this ethical dilemma of having to shred half the chicks every generation, that would be, if people were aware of that, and this is a problem that's being solved with GMOs, that would be go in the right direction. If we were to eradicate Aedes aegypti and dramatically decrease the incidence of chikungunya and dengue and Zika in tropical countries, I think that would make GMOs our friend in a lot of lights. And that's my thinking. We haven't done enough in a good way of good things.
I think there's a lack of definition too of what a GMO is. It could be very narrow, it could be very broad, depending on what source you look at. And so I think that's a problem too, is that when you talk to people, the definition of GMO, it's so wide ranging that no one really has a consensus on what it is, right? Because it could be something like, in the most extreme, you could do CRISPR and you could edit the germline of the DNA of food, but it could also, technically, if you look at the definition out there, it could just be cross-pollinating to plants to get an advantageous trait in the next generation. So that definition is, so one definition in the common conception is like super sci-fi, and then the other definition is things we've been doing for thousands of years. So because there's not really a good definition out there, I think everything gets tossed into the GMO bin, and then it's like, oh, it's scary and bad, but that's, you know, putting everything into the narrow definition, and then, you know, so I think it's a definition problem too. It's like, what do we mean by GMOs, and where is that, like, middle ground between like the super sci-fi germline editing,
Right.
CRISPRs, like that tends to be a little bit frightening to people, versus just like, hey, I'm gonna cross-pollinate this red flower and this white flower because I want a pink flower, you know, because technically they're the same.
Yeah, I was going to say too, I mean, because artificial selection is kind of like a genetic engineering, right? I mean, I don't think most people realize how much our modern fruits and veggies that we're used to seeing, how different they were even like 100 years ago or 200 years ago. I mean, if you just look at old paintings of watermelons, they're mostly like white, like the rind, and like little pockets of the pink flesh that we're used to seeing covering the whole thing now. Bananas were mostly like pits, right, and giant seeds, and a little bit of like
Corn is another one.
corn,
Yeah.
Corn is the
which
the
Jeff has explored.
yeah. You know what?
Yeah.
Yeah. No, I think there is a pretty. It's genetically engineered if you're transgenic, if you're actually bringing
Right.
genes from dramatically, phylogenetically distant genomes into the same genome.
Right. And see, but that definition I don't think is commonly out there, you know,
Yeah.
and so I think that's like part of the confusion and the, you know, it's not sort of
Yeah.
well described.
Any favorite topics? Because we can carry on. We've got a list. We're pretty much out of time.
I have another bio one I could bring up really briefly. Just like a cool little thing. Technically, it didn't happen over the summer. It was March or April. So I'll take a pepper in a second, okay? But
Right.
there's this collaboration between a university in Denmark and a university in India, and this is a biochemistry thing, by the way. They were able to engineer, nucleic acid bases that were double-headed. So they were able to kind of modify the kind of base of the structure, and they could get like an A and a G in the same molecule as a unit. And they did all possibilities. They're able to get like T with T, A with T, and all the combinations there from there. And they actually were able to insert these like double-headed molecules into already pre-existing regular DNA structures. So they could fix like defects that were missing by having a double prong thing and kind of correct a structure that was missing a base, for example. I don't know if they looked at the full long-term stability of these molecules, but I thought that was a really cool thing because you're kind of doubling up the information, right, per unit by having a double-headed thing, and the physical stability of if you have two kind of bases, are you kind of straining the scaffolding of the molecule too much, and how is it going to twist now and
That'd be my
compress?
question.
Yeah, right. And that was my physics thinking,
Yeah.
like, how's this going to work out?
Well, and then, because then the other question I have is, you know, one of the things that signals DNA repair enzymes is defects in the backbone.
Right,
Right.
yeah.
They scan, and if there's like a kink or a twist that's a little weird, they're gonna come in and be like, I could fix this.
I have a hard time visualizing a double-headed nucleotide. No, where's? Go ahead, carry on.
Yeah. So I mean, that would be my question. Yeah, because I don't know, because the twist is it comes from, you know, obviously the hydrogen bonding between the two base pairs. So if you have another one that's like somewhere, I don't know, that would be kind of interesting.
Yeah, I think they did some initial structural studies. I'm forgetting the details of the paper right now, but they did actually measure and simulate the angles of these things, and they were a little bit different from a regular, two nucleotides together, two base pairs together. But it was enough to like cause little shifts or warps here and there in the DNA molecule. And I think that if you had a whole molecule made of these double-headed things, it would look quite different structurally.
Sure. But if
from
it's just
regular
one
DNA.
out of thousands.
Yeah, thousands. It wouldn't really matter that much. But yeah, definitely a cool thing to look at, especially if you like biochemistry. If you think you're going into, I don't know, even organic synthesis, I think would be a cool
So in
thing to
division,
look
would
at.
that be reproduced?
What's that?
In division, would that be reproduced later?
No.
No,
there's no way.
Because you need proteins and enzymes to then, make that.
Yeah, and they wouldn't. that's not a thing that physiologically
Yeah.
would happen. So you could probably put it into a strand of DNA, but it wouldn't be heritable.
Right. Although all those biophysical groups that like to do like information storage in DNA molecules,
Oh yeah,
they
that's
just got
so
an
cool.
upgrade with this molecule. They
Yeah.
can double up their information storage now with this kind of thing.
Yeah.
I thought that was
Coding,
really cool.
coding through DNA, if you've
Yeah.
heard about that, because
DNA circuits.
yeah, it's super cool.
No, it looks like you're actually, putting one nucleotide and basically attaching another nucleotide to the nucleotide, as opposed to having like two nucleotides, two bases. No, one base on top of another base. So you're stacking bases on a single nucleotide.
Yeah, it's a little expanded, but not as much as two side by side necessarily.
Yeah.
So they're able to get some compression.
I think that's a good
some
point.
of
Yeah,
the-
I couldn't see it being like physiologically
Yeah.
that relevant, but in terms of like coding and DNA storage, like that could be pretty cool because
Right.
instead of just 1-0-1-0, now you have all the base pairs,
Right.
and then if you have two, so yeah, you're just like increasing your capacity
Right.
to make like a nice like information storage unit.
Exactly.
Oh, that'd be cool.
Yeah.
A little bit material sciencey there too.
Yeah.
Very cool.
All right. Well, we're pretty much out of time. If anybody has any questions, last chance. Yeah.
I guess since we kind of moved to the topic of kind of DNA and some of this, I have a question, which is when you hear some people talking about going into the genome and editing it to repair for diseases and other things, for a person, let's say we want to do it on a person, would that have to be done before, very early on in the stage of development, before the cells really divide, or when would that be done?
So
Yeah. There's before we were pretty much reliant on embryonic stem cells, and those are the only types of stem cells. But in recent years, we've become really good at inducing pluripotency, the stem cell characteristics, even in fully differentiated cells. So at least in theory, you could take an adult cell, differentiated cell from you as an adult, and reverse its differentiation to put it back into the pluripotent state, and then make some genetic tweaks on that to basically repair whatever genetic issue was there that you inherited from your parents or whatever, or the mutation that occurred. How effective this is going to be, I mean, I think it's a therapy that is in progress. I don't know if we have any other biologists that are ready to chime in.
I mean, I can speak to it because we have adult stem cells basically, which is the idea that we still have cells that can differentiate into any kind of tissue type, and so if you were, I think the thing about because it comes down to CRISPR, right, which is this technology to do DNA editing, and what makes it special is before CRISPR they were kind of thinking about targeted genetic therapies, but those therapies wouldn't be heritable, right? Like it would go through one round of cell division, it would do its thing, but then it would be done. But with CRISPR, the idea is that you can actually go in and edit the DNA, which then makes those changes heritable, right? So all of your future cells will have that change. Your, if you do germline editing on,
It would have to be germline, though.
yeah, exactly. If it was germline, right? So I think one of the things that is like a ethical or like a sort of question is, if you do this DNA editing and then it on the germline and then it's heritable, what if it didn't work exactly as that there's a lot of the error potential is very large because it's not like you give someone the wrong medication and then you're like, oops, we're going to switch that out. If you were to do like editing on the germline and you make a mistake, that's heritable. So I think because like they were doing some germline editing on human cells in China, and then they had a moratorium put on it because they were like, we don't know enough about this yet. Like, we don't want to be messing around with that. But yeah, when they talk about like editing the genome, they're actually talking about going in, replacing a piece of DNA that's not ideal with something that's better. Maybe taking out a mutation or something like that. But we're a long way off from that being like a practical solution to any diseases or anything like that. It's still like very early in development.
Yeah, in case you haven't heard, I mean, last year the big news was a researcher in China. His name was He, and he CRISPR'd HIV resistance into to newborn girls. And it basically did germline editing to CRISPR in the HIV genes, HIV resistance genes on the 2 children. For no other reason apart, for no really necessary reason apart from the fact that he could do it. And huge ethical dilemma, big mess. And I mean, it's really a bad idea because there's no way to be absolutely certain that you're only making a genetic change in one site in the genome. Or the information we have at this point is scant about the off-site or non-target changes that would be occurring through this type of therapy. So it was entirely unethical for this guy to do it, and he did it anyways. And so that's hence the
He's likely to
moratorium.
be executed for it, according to the Chinese government.
He might, yeah.
Might.
You
Yeah,
can get
they
executed
don't-
for having a joint in China.
Yeah, they don't mess around. They don't mess around. So it's talked about, but it's still, right now it's like they mainly do CRISPR on like cell lines. So they've done it on like just isolated cell lines that are used in the lab. They're not put into any living creatures. And that's actually a good application of the technology, because a lot of times if you're studying a disease state, you use cell lines and you can like alter the genetic makeup of those cell lines to see, hey, what happens if we add this medication or do this trial. So that's a good application because it's not going into anything that's like a living, sentient being. So editing on living organisms a little bit far down the line.
I think it's time to wrap up.
Thank you all for coming, and thanks to our panel leaders. So like I said at the beginning, we tend to do this on the first Friday of each month. The topics vary, the speakers vary, so hopefully look for announcements for the next one. I don't know what it's going to be yet, so it's a surprise to us as well. So thanks for coming, everyone.